Oh, I have to do that also, right? Got it. And record. Record on this computer, yes. Continue. Okay. So the next business would be basically maxima, minima, and particular kinds of derivatives, of which there are 4 which are of enormous importance because they came up in physics. And these are called the gradient, the divergence, and the curl. And the Laplacian, which is also called nabla. Nabla is the name of the operator. Laplacian is basically it was a name selected to do Laplace, the famous mathematician. It's an honorific for his name. He was French. In other words, what was I going to say? But these operators were not discovered by or invented by the French. They more or less all of them are to be found in Maxwell's treatise on electricity and magnetism. Maxwell was an extraordinary person because not only did he understand the nature of electricity and magnetism, he actually created the mathematics that was needed to describe it. The empirical or experimental work on electricity and magnetism has a special relationship to this city. The Americans, of course, have strange, what should I say, idols. Benjamin Franklin was the person who is credited with the invention, or with the discovery of the phenomenon of electricity. I don't know whether this story is true or apocryphal, but he was flying a kite. Why he should do so on a rainy day, I do not know. But there was a key apparently tied to the string, and there was thunder and lightning, and the key flashed or gave him a slight shock, some such thing. I don't remember exactly because I read it long, long ago as a child in Bengali translation. I had no idea at the time that I was going to teach in a city with statues of Benjamin Franklin all over the place. You should, a lot of his writings are to be found in the museum, Rosenbach Museum, I think it's called. It's on Delancey Street between 20th and 21st. Can you check where it is? Rosenbach. Yeah. I think that's the name, but
said it was the address. Yes,
what's
2008 to 2010, Delancey Street.
Delancey Street, yes. So that's just one block from Rittenhouse Square. And they have his various items related to him, including things that he wore as a child, which I want to mention, because given the direction of senselessness in which politics is heading, children at his time wore pinafores. Does anyone know the meaning of the word pinafore? P-I-N-A-F-O-R-E. What about a frock? Do you know the meaning of the word frock? Well, this is what one called a dress at the time. So boys and girls both wore pinafores when they were little, and this is not an instance of cross-dressing or any such thing. I'm telling you this because I am certain that some senselessness regarding this will come up sooner or later. Incidentally, from the point of view of mathematics, is there any distinction between a pair of pants and a skirt? Number of holes where? Just a moment. This is not entirely clear. Okay, so let's say a skirt and a pair of pants are both made of some elastic material, which can be stretched and flattened at will without tearing it. Okay, so this is an important area of mathematics which is of direct relevance to this class. So suppose I draw a skirt. It's sort of like a truncated cone, right? So if I were to stretch it out, it will become, I could flatten it, and it would be like a disc with a hole in the middle. A pair of pants, on the other hand, is something of this kind. Okay, so if I stretch the waist, what would it become? It would become like this. This is the waist. And I'm shrinking the legs. So these would be the legs. No, these are flat objects. So a disc with two holes and a disc with one hole. These are topologically different. Why? Can you tell me why? I mean, of course, counting. The first one has two, the boundary consists of two pieces. The union of the inner circle and the union of the outer circle. But the pair of pants has, the boundary is in three pieces, three disconnected pieces, right? So they are essentially different. So, but this is completely arbitrary. I mean, there's the anatomy of the male does not prevent a male from wearing something that is topologically of type 1. This is type 1, and this is of type 2. Topologically of type 2, right? There's nothing to prevent it. Preference to type 1, why? Because it's more comfortable. That's true. Yeah. Yeah. From that point of view, definitely, because of which in very hot climates, people normally wear something that is of type 1 rather than of type 2. Okay. So the okay.
Type 2 is popular with the riding horses.
No, actually, no. It was actually during type 2 became popular during late Roman times, when they started attacking invading the places in Northern Europe where it was colder than it was in Italy. And it was considered effeminate to wear type 2 objects because the barbarians wore them, and there was some Latin word for barbarians which was used to describe what are called trousers or pants. No, because of the cold. Yeah, they still fought less than they still spent less time fighting than they had to spend in the cold. So, but the barbarians wore things that I would call them proto-pants. Okay, so anyway, so this is, But physiologically, sorry. So type 1 and type 2 for garments is one thing. Can you actually figure out type 1 and, I mean, how many types there are of human organisms? How many topological types? Okay, so in order to explain the question, I will do something which most people hear as a description of topology, where people say a donut is equivalent to a coffee mug. Okay, so why is that the case? So suppose I take a coffee mug. This is a fat coffee mug. Fat meaning that it is not, I'm drawing it in with lines, but it actually, there's something like this. So this is fat. Okay. So what I could do, I could gradually reduce the height of the coffee mug and eventually flatten it out so that it becomes like a disc. And that, so it becomes like a disc, and the disc is attached to a ring. And then I can shrink the disc. So all this has to be done pretending that it's made of rubber or some sort of elastic material. We can shrunk and stretched at will, and you're not allowed to tear it. So this can be shrunk until it becomes like a donut. Yes, and this is a solid object. So the task that I give you, if you claim that you actually know your body, you should be able to figure out the topological type of the body, pretending that you are made up of some elastic rubbery material that could be stretched or shrunk at will. Okay, so I'm not going to discuss the question. So I think this should be a standard topological test for people who wish to do mathematics. They have lived in a certain confine throughout their lives. The question is whether they know that well enough. So we have various orifices for excretion of various kinds. So you will have to see how they connect to each other inside. And then the question that you should ask yourself, is there a distinction between the anatomy of those individuals of the organism that correspond to the chromosomal signature XY and those individuals of the organism that correspond to the chromosomal signature XX? These are the predominant kinds, but there are others that are there. As I said, XXX is viable, as is XXY, XYY a little less so. I think there are also XXYY, and then there are mosaics. In these cases, will do the topological types change? So the
so question there is, because in the
well,
example, unless the hole is fully through, does it change?
I beg your pardon?
If the hole doesn't go all the way through, it doesn't create another top thing, correct?
Well, that depends. I mean, there are lots of strange things that can happen. So the point I'm trying to make is that since you have inhabited these premises, since you've come to exist as a fertilized ovum, I think it is in your interest to know what it is like, particularly if you're studying calculus free. Okay? I mean, in other words, if I say find the flat approximation to the surface of your nose at its tip, that should make sense to you. Or count the number of holes that characterize up to homotopy, that is up to stretching. And But that's not enough. You have to see how they are connected inside. So this is not an easy task. And for example, do the eyes, I mean, you might actually try looking at a skeleton, which is slightly simpler. We do have, I mean, there is a whole, we have the lacrimal glands, and all of us have cried at some point, right? So there are holes there too. And then there's the optic nerve that connects it to the brain, and the brain is a rather complicated mess. The best description of the brain as a topological object that I have come across is by Professor Gromov, who is currently in France, but his model of the brain is that it is a graph, which all of you, not all of you, yes, all of you know. No, you took 163, right? Yeah, so it's a graph with a tree-like boundary. So a graph with a tree-like boundary is something like this. At the edge, you have these trees, and in the middle, there are lots of connections, which are the neurons and the axons and the synapses. But the boundaries, for example, the optic nerve, there are two, and they connect somewhere in the brain. Similarly, there are olfactory glands that go from the inner surface of the nose to somewhere in the brain. Similarly, there are the auditory nerves. Then we have our tactile senses, the nerves that come throughout the body. So there are sheaths over the nerves which allow the electrical signals to pass without loss. So in the disease called Lou Gehrig's disease, or what is it called? ALS, amyotrophic lateral sclerosis, in which the myelin the myelin actually decays. So this means that the signals can't reach the extremities, and the electrical signal loses, is lost. So these are, but you should understand your own physiology as mathematically as possible. Okay, so now, yeah.
What counts as part of the body? Does like the food or some kind of part of it, the blood that is
no, you can empty your the blood is in the veins, so I would get rid of all the fluid. Okay, and consider only what looks to be in the solid phase. Okay.
So really similar thing. We'd have to pick one of the holes, and that one holes when we stretch out.
Yes. Yeah.
And then
You might want to go and ask Professor Powell for a model of the human body, since I think it will be much harder to stretch and pull your limbs and see if you can figure out. And then I have another question. Will the types XX and XY fall into different categories, or will it be the same category? So
my assumption.
there are no assumptions. You go and look and see. Yes, so yes, yeah.
But there is another whole, so that is, we also have something. Yes.
Yeah, but it is very important to see. Okay. So, I mean, the reason I'm saying this is because in the debates that occur about such things, sense is completely lacking. So if you wish to call two things equivalent, which word is not used, you first have to have a very clear idea of what the things are and have a clear definition. And then you have to define what on this set of objects. If you use the word equivalence, then what must you define? Those of you who have taken... No. When we talk about equivalence, we must have something called an no. Well, equivalence is a relation between two things. So we have to have an equivalence relation. So unless you can define an equivalence relation on objects that have been defined, it doesn't make any sense to call them the same. So if there is some system of law in which one of the laws says that it is not punishable for an individual of type XY to hit an individual of type XX, then this is clearly an asymmetry. There has to be a corresponding law that says it is also not punishable for an individual of type XX to hit an individual of type XY. This is an obvious lack of equivalence under the permutation rule. 1, 2, if 1, 2 is present, 2, 1 must also be present. Okay, so this is a very primitive way of testing justice. But there are obviously certain differences. There are obviously certain differences in the sense that individuals of type XY cannot lay eggs. Individuals of type XX do produce eggs. Okay. Spermatozoa and ova, are they topologically equivalent? How closely must you look at the structure to understand? For instance, when you study cells, specialized cells, are they topologically equivalent, or are they, I mean, how do you, the functionality, is it reflected in the geometry? Okay, so but this belongs really to this subject, although we are not going to talk about these things, which are they are studied later in a subject called algebraic topology. Okay, but now what I'm going to say is the following. The basic idea about electricity was that it was some sort of a fluid. So it flows. Then one found the sources. There were charges of two kinds, positive and negative. And then one also found that there was something which is fundamentally different, which was magnetism. And one found that there were two different types of poles. We will call them the positive polarity and the negative polarity. And then all of that were brought together in the form of partial differential equations. But before one could produce the partial differential equations, one had to develop this entire setup of calculus of many variables in order to code mathematically what the model or intuition was suggesting. So Maxwell developed all of this. Incidentally, I will mention again all the words that one uses in electrical engineering: resistance, inductance, capacitance, etc., were all created by Benjamin Franklin. In fact, if you go to David Rittenhouse's laboratory, I think you can still see the experimental setups that he had. So, but I am absolutely certain that far more people in the United States know let's say Michael Jackson or Madonna, and than Benjamin Franklin, and certainly no one. Most people in my classes never knew about Feynman. Richard Feynman, yes, whom I should consider one of the most remarkable person who was born and educated in the United States. So idols are chosen on very peculiar principles. I am not sure that Madonna is, I wouldn't use the word pretty to describe her. I mean, the word pretty certainly has a certain range of applicability. It does not include this individual in my use of the word. So,
did you see what was it monsters?
Anyway, so in order to describe the nature of electricity and magnetism, Maxwell came up with these ideas of a gradient, a divergence, and also curl. And the gradient is somewhat difficult to describe, but it is something that is a measure of steepness, which is why it is called gradient. And divergence measures the strength of a source, and curl measures the strength of a whirlpool. So note that if something is turning, like water, swirling in the bathtub or in the commode, in that case, there are in principle two directions in which it can swirl, right? And so this will give two different signs. And that also takes us to the question of orientation. So if I have a triangle, this is made of wires. I can either traverse the edge in such a way that the inside of the triangle is to my left, or I can traverse the triangle in such a way that the inside of the triangle is to my right. These two would give me two distinct orientations. So if I label the vertices 1, 2, 3, in one case I would go from, in one case I'm going in the direction 1, 2, 3. And in the other case, I'm going 1, 3, 2. Note that to go from here to there, I permute the 2 and 3. So one permutation alters the orientation. And two permutations will preserve the orientation. So that means if a permutation is related to another by even number of permutations, these are to be considered equivalent. And those that go from the identity permutation by an odd number of permutations are to be considered equivalent. So 1, 2, 3, 1, 3, 2, but next if I 2, 1, 3 should go there, right? Because I switched 1 and 2, so that is one permutation, right? But that you can see over here. If I start here, 2, 1, 3. Okay? Now, 2, 3, 1 on the other hand, should belong here. Why? Because I go 1, 2 is changed, then 3, 2. Then over here, if I make one change, what can I change? This one. 3, 2, 1 would belong here because that is one permutation from there. But 3, 1, 2 would belong here. A 3-element set has 6 permutations, right? So these belong to one equivalence class, and this belongs to the other equivalence class. And you note that 1, 2, 3, 2, 3, 1, 3, 1, 2. And this is 2, 1, 3, 1, 3, 2. Sorry, 1, 3, 2, 2, 1, 3, 3, 2, 1. So you preserve. So did you understand what I just said? So similarly, if you have a square, you will find that there are 4 has 24 permutations, right? 4 times 3 times 2. So half of them will be odd, half of them will be even. Okay, so this orientation business will come in very handy when we do surface integrals and so on. Okay. Now, these operators that I just talked about, gradient, divergence, and curl, they are all defined. They are defined using the partial derivative operators. Okay, but you should understand them as taking as input. So they are functions essentially. So they take as input something called a field, and they produce as output either a scalar or a vector. Okay, so all of them act on fields, either on a scalar field or a vector field. So we will have to talk about a field. So the field is this is not a very difficult notion. You already know about it. So for instance, suppose you have some sort of a surface which is being heated from underneath, or a room where there's a heat source somewhere. Okay, you can measure the temperature at every point. So each of these is an example. This is a 2-fold, that is a 3-fold. So at every point, oh, what did I do? 3 dashes down the right. Yes, I see that. Ah, okay. Okay. So specifying a scalar field, such as the temperature, would amount to specifying a real number at every point of the k-fold that I have. Okay, so a scalar field P would amount to, in n dimensions, x1 up. Actually, let me do it in lower dimension first. So corresponding to the example. In this case, I have a point x1, x2. So this goes to x1, x2, P of x1, x2. From R2 to R2 cross R. So I am saying that if P is thought of as the temperature, this is saying that at the point x1, x2, I have the temperature, sorry, not R2. Well, okay, R2 is fine. So this is not a manifold, but the entire plane. So at every point in the plane, I am specifying at which point of the plane I have which temperature. Okay, you could think of the temperature in terms of the intensity of a color. Okay, so for instance, in 3 dimensions, we could do the same thing. Again, let's call this C. So x1, x2, x3 goes to x1, x2, x3, C of x1, x2, x3 from R3 to R3 cross R. What happened? Which didn't quite fit. So this is an example of a scalar field with the temperature. Okay. Another thing, a scalar field could be if you have an sort of a heterogeneous liquid in some sort of a aquarium, the density locally can change from place to place. Okay. We could consider what can we consider? We can consider our veins and measure that's not actually scalar field.
So like the x1, x2, x3, they represent the axes?
No, x1, x2, x3 represent the coordinates of a particular point with respect to some chosen axis. Okay. So x1, x2, x3 is a point in R3. So the coordinates of a point of R3 with respect to some set of axes. Okay. So for instance, let's take something like this square. So at each point, so at 0, 0, the temperature is, let's say in centigrades, let's say that is 0. At 0, 1, temperature, let's say, is -2, and so on. So that is what this is saying. At every point, you are assigning a particular value. I beg your pardon?
In the second one,
0, 1. That's a 1. Okay. So this way, at every point, I know exactly there's this number. Since a number means a member of the field, which is R, so that's a scalar. Okay. But on the other hand, we also need to deal with the idea of a vector field. The vector field tells you that at every point, you have associated a vector. Okay. So let's take R2 and so let's say we have poured water on some sort of an inclined surface, so the water is flowing. But it's a thin film. So it's effectively a two-dimensional structure. But the water is flowing at different rates at different places. So what I want to do, I can measure the velocity of the water at a particular point, and I can assign to that point that particular velocity. Okay. So in this case, I would have to say, let's say that the point 0, 0, the water is flowing at the rate of say, let's say 1, 1. Sorry, at the rate of so the velocity vector of the water particle at 0, 0 is 1, 1. So let's see. Why is it not responding to my finger in the same way?
The press on it.
Press and then slide. Okay. What's that symbol?
It's 3 lines.
Let's see. How do I make it go away?
This one probably is the small little.
No.
Done.
Oh, done. Okay. I need more devices. So I can see what it is.
That's a magnifying glass.
Yes.
So when you hit on it,
But the magnifying glass has a plus in the middle.
so
Done means okay. So the hieroglyphics are not easy to decipher. I mean, no one has told me what the value is.
On computers, the plus generally is in and the minus is out with a magnifying line. But why does it give it?
First of all, it is, well, yes, if you recognize it to be a magnifying glass. This is I suppose, is a magnifying glass, but I have another device, which is this. It's not a magnifying glass at all. It is a Fresnel diffractor. But it does magnify. So why would I choose this rather than a rectangle as a symbol for something that...
It's a question, why do they use a floppy disk to represent saving?
I didn't choose it, so don't ask me. So the... No, I understand. It's an arbitrary choice, and it is stupid to call it intuitive, which is what all these sort of techie people say, and it really irritates me when I go and talk to this iPhone people, Apple people, who have named themselves members of the Genius Bar, or the Google propaganda, where someone comes and says, oh, it's all very intuitive. It means that you have a certain kind of superstition to which I don't subscribe. So this is a very simple question. If you see the picture of a human-looking object on a door, does it follow logically that on the other side there's a toilet? No. All you know, there could be a well. You open the door and you are pushed to your death. So unfortunately, it is not an arbitrary value is attached to jumping to conclusions based on very insufficient information. And this is considered intelligence, which of course is stupid. So, but I don't expect this to change. I will give you another example of this, but this is the fault of senselessness coming from psychology department. So I will write 1, 1. This means at the point 0, 0, this velocity of the particle has a representation 1, 1. Okay, let's say at the point 0, 1, the velocity of the particle has the representation, what shall we make it? 1 minus 1?
Sure.
Okay, what does it mean? It means that the water is flowing at different speeds. 1, 1, of course, will be this vector, because the vector that goes from 0, 0 to 1, 1. So 1 minus 1, x component will be 1, y component will be minus, right? So x component is plus 1, y component minus 1. So that would be like this. So water here is flowing in that direction. So I can put arrows everywhere to indicate how the water is flowing. Okay? So that is called a vector field. And the vector field in R2, we will give, I've forgotten what notation I used in the notes. I have absolutely no recollection whatsoever. C or something. Yeah, just see what. Maybe C.
I don't know what that is. It's an upside down triangle.
No, upside down triangle is the gradient.
Oh.
That's not the. It is acting on the gradient. You don't take the gradient of a vector field. You take the gradient. You find water taking the of alpha beta. Is that what you use for vector fields? No. If you will see the upside down triangle dot something. DT. No. See, look at the upside down triangle and then a dot and then the next symbol. Yeah. Del. No, no, no. Differential operators, yes. So, but what is it acting on? What is being fed into? So you would have upside down triangle. Yes, yes, those. But let me see. Next page. This next page also doesn't have it. Yeah, alpha. Alpha is a vector field, a scalar field. Next page. Yeah, alpha, beta. Okay, that's fine. So it's on alpha.
Because this is what I was talking about when I was talking to you with the DET.
Yes, that is true, but this is operating on beta.
Okay.
Okay, so alpha, beta, gamma, these are vector fields. Okay, so in R2, it would be x1, x2 going to x1, x2, comma, let's say x2, x1. From R2 to R2 cross R2. So note that look at the table now. So this is R2, right? This is a section of R2. So at every point, there is a tangent plane. The tangent plane is the plane itself. So at every point, there is a copy of R2 attached. So there's an infinite surface with an identical infinite surface attached at every point. So do you understand what I'm saying? So, I mean, if I had a bunch of sheets of paper, let's see, do I have sheets of paper here? This will do it. I don't know this, but
Are all of the fields that are on every single point are going to be used to show the vector?
no, it's okay. So I will explain to you. So these are sheets of paper which are supposed to be the tangent planes attached to every point. So the vector, the second component, lies in the tangent plane that is attached to that particular point. So this is important to understand. So this is the square. So at this point, there is something attached. 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 Okay? So I have infinitely many infinite planes attached to the basic infinite. They're all tangent, which means that they must lie flat. And the vector lies in that tangent, and it is attached to that point. This is what you need to understand. Okay, so this is easier to. So this vector at the point 0, 0, it is of size 0. So alpha of 0, 0 is equal to 0, 0, 0, 0, right? Alpha of 0, 1 is equal to 0, 1, 1, 0. That means we have spent 1 hour. Okay? Clear? Yeah. This I could, you see, it's this, I'm teaching in this horrible room with nothing in it, but at least there's a big blackboard. This sort of thing should be done where one has immediate access to lots of objects, which I'm improvising with all sorts of things from my bag and from my pocket. But if you take an ordinary magnet and put iron shavings around it, you will see the iron shavings organize themselves along the field lines of the magnet. I don't know if you've done this experiment in physics labs. You have at home. So So that means at each point, there's a value of the magnetic field. So if there's a water flowing, you will get a certain value of the velocity. Actually, the flow of liquids and the flow of traffic is very similar. So for instance, if you consider the flow of blood in the circulatory system within the human body, and if you look at the flow of traffic, let's say in Philadelphia, you will see that the dynamics are very similar. So the flow will be slower if the veins are very narrow. But if blood is compressible, if it is incompressible, then it will have to speed up. Okay. For incompressible fluids, if the path along which you are going is narrow, it has to speed up because otherwise it wouldn't work.
So I know blood is, so there's something called non-clean fluid, which is explanation for blood is cornstarch mixed with water. When you hit it, it kind of turns into a solid.
Yeah.
The opposite is true for blood. If you put pressure on it, it moves faster. So,
Yes, so it has a coefficient of compressibility. Yeah, so I mean, you can, what should I say? You can model it as an incompressible fluid as a first approximation. But on the other hand, if you take aspirin, then the viscosity becomes lower. So they call it a blood thinner, a very strange name, but so it changes the physical characteristics. So there's a subject called statistical mechanics in which you can actually calculate these macroscopic qualities, and they arise as expectation values of certain observables. Okay, so let me try to draw this. So at 0, 0, this is 0. At 0, 1, which is this point, it is 1, 0, right? That means it's this vector. At alpha of 1, 0 is equal to 1, 0, 0, 1. So at this point, 0, 1. 0, 1 is this vector. So it's this vector over here. At the point half, half, this is equal to half, half, half. This won't fit. At the point half, half, it's equal to half, half. That means at this point, it's this. Okay. At the point 1, 1, it's equal to 1, 1. So at, sorry, I forgot the first coordinates. Just a moment. Is equal to half, half, comma, this. At the point 1, 1, it will be 1, 1, comma, 1, 1. Which means at this point, it is this. This is roughly of the two components are 1, 1. Okay, so this one is 1, 0. This one is 0, 1. This vector is half, half. This vector is 1, 1. But they are attached to those points, which means they lie in that tangent. Okay. So these vector fields will be the inputs for certain machines we shall define. Machines, you know, are functions or operators. One machine is the gradient machine. A gradient machine takes as input scalar field, and yields a vector field. This is divergence, which takes a vector field and yields a scalar field. That takes a vector field and yields a vector field. Okay, and this measures the strength of source. This measures the rotation of field at a point, roughly speaking. And this measures the fastest increase. Okay.
All done on
It's all done in the notes. I mean, the explanations are not given, but the calculations are given. So the point of view that I'm taking is that you first must learn how to calculate. And then you will gradually come to understand what is going on. Okay. So for instance, if I have, and I have sent you one of these Eugene, I keep on forgetting his name, Kurtianovsky. Can you see how is it spelled? Actually, I will let Max pronounce it for me so that I remember.
Or was it sent?
Yes, I sent it in an announcement.
how long ago?
Just come here with your phone. I will ask you to Eugene plus physics video. We'll put that in Google. Eugene plus physics video. And tell me what the last name is. I keep on mispronouncing the word.
Eugene Hutoriansky.
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 Hutoriansky, okay. Eugene Hutoriansky. So he has a video on gradients, divergence, and curl, which you should all watch. I sent it to you already. Okay, very beautiful video, actually. Yeah, can you try to find it? Shall I write it down over here? It is in an announcement, the 2 or 3 announcements ago. Put in Google, put Eugene, what is the name again? Hutoriansky. Eugene Hutoriansky, K-H-U-T, K-H-U-T-O-R-Y-A-N-S-K-Y, math videos.
And spell last name again is
K-H-U-T-O-R-Y-A-N-S-K-Y, math videos. Eugene, K-H-U-T-O-R-Y-A-N-S-K-Y. No, it's not coming up. It is here. Can you turn your computer and can you play it for a little bit? Let me see.
settings.
I cannot find it in the
No, I sent it. I sent it not long ago. I know. Before, right after exam 1A, I think. No, I sent it to 271.
Video called Divergence and Parole.
Yes, 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 that's the one.
Okay, it's in the announcement.
It is in the announcement, yes. Yeah. And no one looked at it. Yes, it's a very good video.
The version kernel.
Yes, 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 that's the one.
Platform.
Someone been in the Discord about odious truths.
Yes.
Yeah, that's fun.
That was long ago that I sent it.
No, the one with it was like last class. Sent the Klein bottle.
Yeah,
And so it was actually kind of interesting because in that he goes in, there's some handedness in the way he figured out the best way to explain the fourth Klein bottle setup or whatever. So, and he kept showing like all these crazy things because he couldn't figure out there were 4 different ways the Klein bottle should have been arranged. And they like he could not understand the last setup.
I see.
And last setup is for whatever reason, if you change like the side it's on, it will make the same looking Klein bottle, but it's a different Klein bottle. This is a weird way to think that.
Probably he made 2 Klein bottles with different origin. I'm not sure. I mean, I haven't seen it, so I don't know. But
Is it? Is the one I was talking about? Is it the?
No,
Okay.
yeah. Please watch it to the end. It's very good.
Yeah, I will throw that.
So Khutoriansky. And Eugene is what? Evgeny? In Russian. I mean, or Ukrainian, both they should be similar. Okay. Yeah. But you should look at it because it actually describes it very well, very nicely. Okay, so these are 3 operators. I drew them as machines, and then there's a Laplacian one also. Let me erase this one because it's serving no purpose. The Laplacian is this one. It can take a scalar field and give you a scalar field. Or it can take a vector field and give you a vector field. So we have scalar to vector, vector to vector, scalar to vector, vector to scalar, vector to vector, scalar to scalar, vector to vector. Okay, so all 4 possibilities. Okay, and all of these come up in describing motion of fluids or electricity and magnetism. But experimentally or theoretically also? Okay, so if you have a point charge, it endows its surroundings with the electric field. That's how it makes its presence felt. Yeah, the potential actually is basically something that it's a second order concept. We want to understand the fields as gradients of potential. So that means the field is higher when the potential changes more quickly. Okay? And you will see later on when you study moving charges or currents that you will have an electric field and also a magnetic field in its vicinity. Okay, so electricity and magnetism are very closely related. And light actually consists of electromagnetic waves. There was a great deal of confusion and controversy regarding the nature of light, whether it was particulate or whether it was field light. And now we know that depending on how you look at it, it can behave like either. Okay? So this is the first business that we need to understand. That is water. What does it say? Pure leaf.
It was a green tea.
Ah,
The tea in it.
okay. So your job would be to calculate with these. Now, all these fairy tales that I'm telling you will help you understand these as physical objects or geometric objects. And if you look at the videos, you will get a better idea of what the objects are like. Okay. And let's see. There is also a very nice paper on fat Möbius strips and fat Klein bottles that I saw. Yes, fat in the sense of what I produced with a belt the other day.
Oh, flat. Okay.
Not flat, fat.
Fat, like FAT.
FAT, because a Möbius band is not supposed to have any thickness, but what I did with my belt does have thickness. You did it with the belt also. Yeah. So that's an example of a fat Möbius band. But fat Möbius bands occur, I mean, there are sort of deformations of those that occur as minimal surfaces. And there's a very nice paper with very beautiful pictures by a German guy, which maybe I should have included just to show you what it is like. Okay, so your first job would be to get some sort of an understanding of these things, but you should be able to calculate these things properly. Okay? The understanding will gradually come and will deepen over time. But the ability to calculate can be immediate. And then the next kind of thing that we should study are these ideas of maxima, minima, extrema, and Taylor's theorem. Okay, so we are still in the realm of differential calculus. But there is a solved exam for this one. Oh no, this is 1C, right? There are no 1C.
There was no 1C. So
1C and 2A don't exist. So 1C, there's a painful problem at the end, which involves analyzing the nature of the extrema. But you should always understand that in order to reduce the number of possibilities, one always has to look at symmetries. And symmetries define equivalence classes. And one does not need to distinguish between members of an equivalence class. This is the point that you need to understand. So reduction of work amounts to recognizing symmetries. And although I played the game with Max and Arash, who is not here, I think it is worthwhile pointing this out because this will reduce your work. Who wants to play tic-tac-toe with me? Okay. Well, actually, tic-tac-toe, we will play double tic-tac-toe and I will beat him also as I've beaten you in the past. So in tic-tac-toe, so listen to the question very carefully. How many possible initial moves are there? No. How many possible initial moves are there?
possible. Like
Initial moves, yes. Oh, you were in 163. So you've seen this, yes. No, okay, so let me repeat the question. How many possible initial moves are there? No, 9. There are 9 possible initial moves. How many inequivalent initial moves are there? That is 3. Now, the 3 of you understand, but you never saw this before, right?
It makes sense. It makes sense.
No, why are there 3?
Because, like, well, as they affect the game, it'll, like, the very center of one of the edges of the corner, like, you just like rotate it.
Yes. So that is exactly the point. So in other words, the symmetry over here is turns by 90 degrees. So if you turns by certain angles, so if you These four are related by terms of 90 degree, right? So these four are also related and should be thought of as single equivalence class. The middle is in a different category. So we have three equivalence classes. So there are exactly three in equivalent modes. So if I want to analyze the game, I have to think of exactly three possibilities. Either someone plays here, or someone plays here, or someone plays here. Then this breaks the symmetry. So in the next stage, the tree will have 5 branches because there are 5 inequivalent moves. 1, 1, these are equivalent. 2, 2 equivalent. 3, 3 equivalent. 4 and 5. So this will give you the entire tree. And the entire tree shows that every person, every player has a strategy to force the game to a draw. Okay? So when you analyze your maxima minima problem, suppose you have 64 points to check, but you don't really need to check 64 points. You have to divide it into equivalence classes depending on what is it that you're trying to test. Is this clear to everyone? The idea? But we will see how you apply it to that problem. I think it's 3B or something like this. Okay? Any questions up to now? And the people, who are the virtual people today? I don't even see. Cesar is there? No one else. Okay. Any questions? No? Okay. So I will not do any of the actual details today. This is just to tell you roughly what this is about. So next time I will calculate a bunch of these things, but it's also done in the notes. So read the notes, but before you read the notes, actually look at the video. Yeah. Yeah. Well, first, put makeup on your exam if you need to. And then do all these. After that, you should decide on your own topological type.
Oh, us.
Yes. You must learn enough physiology to make sense of the question and then see what you are topologically.
If the first one was 1 and 2, like a skirt is 1 and
a skirt is equivalent to an annulus. A pair of pants is equivalent to a disc with 2 holes. An annulus is a disc with 1 hole. I mean, all disc with 4 holes. No, we are 3-dimensional objects. We can hardly be discs. I didn't ask you to. We are solid objects. No, even then you would get something like a solid torus, which is different from an annulus. I mean, we are 3-dimensional objects. That's why we were 2-dimensional objects. Yeah.
Okay.
What is the topological type of your shirt?
It's a disc with 3 holes. If we're going up the same.
Yes, we are doing this. Is this disc with 3 holes? 2 for the sleeves, 1 for the head, and 1.
And I guess we pull this one out. I had some equal the head. 1 for the waist, you pull out, you have the head.
Yeah. So it's a cylinder with 2 holes, and then you flatten the cylinder out, so that will give you 3 holes, right? So you're wearing a disc with 3 holes and a disc with 2 holes.
And then. What are these?
And a disc, 2 discs, actually 4 discs. 2 solidish discs and 2 more pliable discs, the socks.
3 discs.
Shoelaces
3 discs.
can be reduced to a point.
Just 2 holes, just 2 holes. Oh, actually, no, that is.
Hmm? Oh, yes, yes, yes. If you take the shoelaces off, it will be much, much more complicated. Yes, it is with many holes. Yeah. Mine are simpler. Mine are discs. In fact, it is made of rubber.
So we could actually do it.
Hmm? I am wearing Crocs.
Oh, yeah, and you're wearing Crocs that don't have the speed band.
Yes, yes. I am wearing Crocs. Oh, the white ones that I used to wear when you were a student are upstairs in my office. Oh, that reminds me. Do you know where Colin Pescaro is? Do you remember him? You sat in the front. He used to sit over there. Is it at all possible to find out if he's at Temple? Do you have any contact with people at Temple? I mean, meaning the CCP people at Temple.
I mean, you might be in one of the old servers.
But he's probably not going to look at them. I have to just
Well, if
look
he's
at
an
him.
old server, we can find him and send him a message. And if he's ever on Discord.
He was on Discord at some point, yes.
So.
It was a very lively class. No, you wouldn't know.
You know it's me, this company. So.
I will go upstairs and look through my old agreement forms to see if I can locate him. Okay, so incidentally, actually, what is the topological type of your shoes? How many holes do you have? It's a disc with how many holes?
7, 14 and the tongue.
Many, yes.
Yeah, look at this. Yeah, the tongue is it. Yes. So 14. I don't know. These go through or not. No, mine goes through. So it's nothing through the field. So.
So, but that is the topological type.
This is 14.
Yeah. I mean, I wouldn't ask you to integrate something over the surface of your shoe, which would be a pain beyond imagination. But on the other hand, I think there's a problem with 2 holes. Now, looked at from this point of view, the whole idea of cross-dressing sounds an absurd triviality consisting of a quarrel between, do you use a disc with 2 holes as opposed to a disc with 3 holes?
Except for people that get sexual pleasure.
Yeah, that we can't quite codify yet.
Maybe what brains they do that.
Yeah, in other words, but it's some sort of an attachment or imprinting with discs with 2 holes as opposed to discs with 3 holes.
2 holes, right?
Like item description.
Yes. Oh, but I mean the
Just with 2 holes. Makes sense, right?
a bra,
A bra.
pair of bras. It's 2. It's like a figure of 8.
It's a figure 8.
Yeah. Yeah, because the discs would just shrink into points.
Well, yeah.
Straps, yes, but they're true. Unless if they're attached by buckles, in that case, it will just be a point. Meaning that it will be a disc. A disc is just a point, a stretched out point.
What about the building?
The belt.
The building.
This building? This building belongs to the disaster equivalence class, which he refused to define.
Stretch it out. The straps.
No, if the straps are attached permanently, then there's only one clasp at the back. So if you take the clasp out, so then there are two circles. The rest of it is just some sort of a disc,
Okay.
which you just squish to a point. It is.
Why wouldn't that just be a disc with two points?
No, it is.
It is.
It is
Okay,
effectively, yes.
okay.
Yes. A disc with two holes. I mean, if you squish the, you see, this is a disc with two holes, right? But I can squish it. And further and further. So eventually, that's the skeletal type, basically. So, I mean, it is absurd to quarrel about a figure of 8 and a figure like this.
I was just surprised you said figure 8 because it was
I mean, I went a little further in my squishing and collapsing. But the point is that if people fly at each other's throats about things of this kind, I think it is the discussion of the kind that I am engaging in would do a lot to throw cold water on the animosity and bring sense by pointing out the utter triviality of such discussions. Not to mention the fact that the Roman, what should I say, the soldiers, yes, but that was a very specific name. But all the members of the Roman fighting sets, they would consider what men wear nowadays as effeminate and barbaric. Yeah, and so things change. And that in the US not very long ago when Benjamin Franklin lived, there are, I mean, I think, if I remember correctly, some of the pinafores are also. Pinafore, Pinafore, look it up. Yeah, yeah. The word dress in earlier times was a class name as opposed to a name of an individual object. Did you find the word?
Yeah.
Pinafore. That's Russian.
Yeah, no. And how it's
You still didn't find it?
You said
Pinafore.
Yeah, okay. For some reason, you have RL instead of R, so.
Yeah.
Okay, that was not what I was expecting when the images.
But everyone wore those things as,
So this is, we just had all of that pop up. What I'm learning now.
yes. Okay, so these, I mean, I told you that I have a problem where you have a sphere, solid sphere with a hole that looks like a donut inside. And you will have to integrate something over it later on.
This exam is going to be fun, guys. We don't have one to work off of.
No, that exam actually, that is 2C. 2B and 2C exist.
But we're at 1C right
Yes, 1C doesn't exist, but 1C is not very difficult.
now. Okay. So, that's the one.
Is there two seats? I don't know.
Yes, there's a 2C. 2B and 2C exist. It's only 1C and 2A that don't exist. But 1C and 2A are not very difficult. 2A is only line integrals. And 1C is this maxima minima business. And there's gradient divergence and curl and Taylor's theorem. The Taylor's theorem problem is absolutely awful. But you should do it because if you just keep at it, you will get the answer. And it's worth however many points.
It's 41.
No, one must always shoot as high as possible. Yes, yes. You should always shoot for 51. This is not very difficult. Yeah, there's nothing. These don't bite you. These don't cause you stress. I mean, they're just inanimate objects. I mean, when Rivera thought of me as a mixture of a monster and a computer, then I could understand that there was some reason for stress. But since you know me now, oh, but the grading is, I mean, you all know how I grade.
So, yeah, that definitely was the first couple times.
So, okay, shall we call it a day? Yeah.
Yes. If you have someone
How-
go home to and say happy Valentine's Day.
Let's see, where do I have to stop the recording? I forgot.